Moving on to the next example, we got a boat and it's traveling at 50 kilometers per hour north, and it encounters a current from the east at 15 kilometers per hour. What is the resultant velocity of the boat? So let's start this question off by drawing each scenario separately. So let's start off with the boat. And the boat is traveling at 50 kilometers per hour north. And let's draw a compass here that we can refer to. So this is north, west, south, east. So a boat is traveling 50 kilometers per hour north. Notice how this is a velocity, which is a vector, because the 50 is the magnitude and the north is the direction. So we can draw this as 50 kilometers per hour north. Now let's deal with the current. Now what do they say about the current? The current is going at 15 kilometers per hour and it's coming from the east. It's coming from the east, so it's going west. You got to watch the wording of the question. The current is coming from the east, so it's going towards the west. So the current is 15 kilometers per hour west. And we can draw that vector like this. 15 kilometers per hour west. This is 50, this is 15. These may not be necessarily to scale, but they should be. Now to find the resultant velocity or the resultant vector, we would just add these two vectors together. So let's start off with the boat vector. So the boat, let's call this vector B. Represents the boat. So this vector B is 50 kilometers per hour north. And then let's add this current vector to it. And let's express this vector here as C for current. And the current is going at 15 kilometers per hour west, towards a west direction, coming from the east. So the resultant vector we would draw by starting at the tail of the first vector and ending at the head of the second vector. So this would be our resultant vector, or the resultant velocity of the boat, and let's call this V here. This represents the resultant velocity of the boat. So the boat is going in somewhat of a northwest direction. We don't know the exact direction yet, but approximately it's going to be going this way. So we have to find the resultant velocity. Now, velocity, if you remember, is a vector. And a vector, if you recall to the definition of it, contains two things. What does it contain? It contains a magnitude, and it contains a direction. So we have to find the magnitude and the direction of this vector V. So let's start by finding the magnitude. Now, if you notice, this scenario here represents a right angle triangle. It's a right angle triangle, and this length, or this magnitude, is 50, and this magnitude is 15. So since it's a right angle triangle, to find the magnitude of V, we can just apply Pythagoras theorem. So basically, a squared plus b squared would equal c squared. So the magnitude of v squared would equal the magnitude of the boat squared plus the magnitude of the current squared, which represents the magnitude of these vectors. So the magnitude of the boat is 50 squared, the magnitude of the current is 15 squared, and we are solving for the magnitude of v squared. So doing all this, once we isolate for the magnitude of v, so we add these two expressions and then we square root it, we would get the square root of 2725, or 52.2 kilometers per hour, if we do it in the calculator. Now, the second thing that we have to solve for, because we're solving for a velocity, we have to find the direction of it. We found the magnitude here of 52.2 kilometers per hour. Now we got to find the direction. So to find the direction, let's solve for this angle theta here. So if you think about it, since this is a right angle triangle, we're dealing with theta and we have the opposite side and the adjacent side, so we can use the tan ratio. So tan theta is basically equal to the magnitude of the current over the magnitude of the boat, because the current is the opposite side and the magnitude of the boat is the adjacent side to the angle. So if we isolate for the angle, we would have to find the inverse of the tan inverse of the magnitude of the current, which is 15, over the magnitude of the boat, which is 50. So if we input that in the calculator, we would get an angle of 16.7 degrees. Meaning that the boat, that if we go back to our compass, the boat is going this way, and the angle here is 16.7 degrees, this angle right here. Okay, it might be kind of small, you might not be able to see, but basically from north to here, that angle is 16.7 degrees. So to express that velocity, basically the final velocity, the resultant velocity is 52.2 kilometers per hour, and the direction would be north. We start at the north and we're going 16.7 degrees west, towards the west side. So let's do a recap of what we did. So we have to find the resultant velocity of a boat that's traveling 50 kilometers per hour north, and it encounters a current from the east, so the current is going west at 15 kilometers per hour. So we took these two vectors, added them up, and we have to find this resultant vector, or this resultant velocity. So because we have to find a velocity, we have to have a magnitude and a direction. To find the magnitude of v, we just applied Pythagoras' theorem with the magnitudes of the current and the boat. Solve for the magnitude of v, and we got 52.2 kilometers per hour. Then to solve for the direction of the vector v, we solve for this angle theta here using the tan ratio. Inputting that into the calculator, we got an angle of 16.7 degrees. So the resultant velocity of the boat is 52 kilometers per hour in a direction of north 16.7 degrees west.